looking at the characteristics yesterday. We're going to continue on with that in 1.2. So kind of flashing back or recalling from yesterday, we started looking at graphs of some polynomial functions. And one of the polynomial functions that we looked at graphing was x cubed. And if we got a quick little sketch of that, it's going to do something like this. Okay, we talked about how it went from quadrant 3 to quadrant 1. And that's a basic cubic function. Okay, now it shouldn't be that hard to think about or to realize that they're not always going to be that easy. We can get a cubic function that could look, say, something like this. Okay, it still looks very similar to a cubic function. It still has the same end behavior. It's still going from quadrant 3 into quadrant 1. But the cubic function may have an x squared term, may have an x term, which affects it a little bit. So it has these waves here. Okay. And what we're looking at is we're going to eventually be starting to look at, well, these points here and figuring out where our x-intercepts are and looking at how we can get different graphs of these functions, how we can determine the graph given the equation. So if we look at our graph, when we look at this high point, this high peak right here, if we kind of forget about everything else that's around it, and we looked at it kind of what we would call it last year, we'd call that our maximum value. So what we can do is we can call that a local max because it's the highest point in the area. And if we look at the minimum value over here, similarly, we can call that the local min. Okay, so right now what we'd be doing for that is looking at, all right, well, if we had some restrictions like we saw in the homework question where we had our domain being 1 to 10 or 0 to 10, we can find a local max or a local min within our domain. Okay, and similarly, we could find certain zeros within our domain, depending on how we set that up or how we define it. So we're going to be looking at doing things like this in the near future. Okay, so if we remember calculating first and second differences, if we have a linear function, so 3x plus 2, we get a table of values, we calculate first differences, we know that we recognize or we get that the first difference is constant. So a linear function has a constant first difference. And from yesterday, we can classify a linear function, or we can say it has a characteristic that it's a first degree. Okay, so a linear function, degree 1, constant first difference. If we go and look at a quadratic, say y equals x squared, we know we take the first difference, we take the second difference, and then we get a constant value. So we say a quadratic has a constant second difference, and those are a second degree polynomial. So we're starting to get a pattern here, and we can extend that into a cubic, and we can say that a cubic, we take our first difference, we take a second difference. When we take the third difference, we get a constant value. And so a cubic has a constant third difference, and it's a degree 3. Okay, so our pattern works, and that is true. And so what we can say is a polynomial in the form and I'm going to give the general form again. So we'll say an x to the power n plus an minus 1 x to the power n minus 1 plus, and all those dots, a1 x1 plus a naught. So the general form of our polynomial. Okay, from that, what conclusion can we say about the constant difference? What constant difference will this polynomial have? We can say it will have the nth constant difference. there are a few more patterns that we could find looking at tables of values, and this leads us to finite differences. Okay, so tell us that, so finite differences, it tells us that for a polynomial, function of degree n, okay, where n is a positive integer, so positive integer means 1, 2, 3, or 4. We're not dealing with negative numbers. We're not dealing with decimals. So where n is a nice positive number, okay, there's a few characteristics about the nth difference. Okay, so what is the first characteristic that you guys recognized about the nth difference? Okay, for the three examples that we just saw. So we recognize that the nth difference of an n degree polynomial, that nth difference, we recognize that it's constant. Okay, there are a few more patterns, and if we would have done more examples, you would have seen this. You would see that that nth difference, it's constant. It's also going to have the same sign. Okay, same sign as the leading coefficient. Okay, so it's going to have the same sign as the leading coefficient in that polynomial. Okay, and maybe one that you probably wouldn't have recognized as easy, the value of the constant difference. So what we get in the third difference, okay? That value of the constant difference equals, okay, a subscript n. So what is that in terms of our polynomial? The leading coefficient. So it's going to equal an, which is our leading coefficient, okay, times n factorial. So n factorial, or n with a little exclamation mark, that actually is a mathematical notation. And what that means for n factorial, what that means is n times n minus 1 times n minus 2 times all the way down to times 2 times 1. So for example, if we had 4 factorial, that means 4 times 3 times 2 times 1. You will be asked, or you'll see, you'll be given a polynomial, for example, that looks like negative 3x to the 5 plus 4x cubed plus x minus 10. And I could ask you, what is the value of the constant difference? Okay, so looking at that polynomial, what difference is going to be constant? The fifth difference. So it will have the fifth difference okay, so the fifth difference will be constant. What is going to be the value of the constant difference? Okay, so to find the value of our constant difference, sorry, we have to go back to our theorem, and that'll tell us that the value of the constant difference is going to be our leading coefficient times n factorial. So if we look at our equation, what is our leading coefficient? Leading coefficient is -3. What is our degree? 5. So it'll be -3 times 5 factorial. So in our calculators, let's go 5 factorial and then multiply that by -3. So if we go through and -3 times 5 factorial, we should come up with -360. So if we had a table of values, and if we took our polynomial, filled out a table of values, and started doing first differences, then second differences, then third, we'd have to go all the way over to the fifth difference, and we should get a value of -360. Okay, so you can kind of see why doing or having a theorem is a lot easier than doing the fifth difference of this giant polynomial and getting a value of -360. Okay. Okay, so a second example, you could be given a question that looks like this. You're given the fourth constant difference of -72. What is the leading coefficient of that function f of x? So how can we use finite differences to set up this question? What's that? We're going to just plug it in and rearrange. So we have our value equals our an times n factorial. Take that. What do we know? What values do we know? So we know our value is -72 and our n value is 4. Okay, what is 4 factorial? 24. And we can get our leading coefficient by itself by dividing by 24. What is our leading coefficient? -3. Okay, so we know that, or we can determine that our polynomial function that gives us a fourth constant difference of 72 is going to start out looking like -3x to the 4. And if I gave you more information, you could start building a graph and going from there.